So we talked about internal heat. Internal heat is the amount of energy that's stored in a substance because of all the molecules bouncing around. So we can transfer heat to and from a substance by increasing its internal heat, decreasing its internal heat, its sensible heat, by simply applying an energy source. However, there's another kind of heat, another kind of energy exchange that turns out to be very important. It's called latent heat. Latent heat is kind of a difficult term to remember because it's sort of implying that there's energy that's stored in something that hasn't been released yet. But in a way that's true. We're going to look at how energy changes when water changes from one phase to another, when it goes from liquid to vapor, or from ice to liquid, for example. So before we looked at the amount of energy it took to raise the internal energy of 1 gram of water 1 degree C, and we said that was a calorie. How much would it take to melt or to evaporate water? So we can look at how much it would take to take 1 gram of water and evaporate it. So we want to turn 1 gram of liquid water into vapor water. How much energy would that take? Right? It took 1 calorie to raise the internal temperature 1 degree. It turns out to evaporate this water, it takes 590 calories. 590 calories to evaporate 1 gram of water. So it takes a tremendous amount of energy to evaporate water. And we're going to find out that when that vapor goes back into a liquid, that energy needs to be conserved. So it's released again. So when we want to evaporate water, we have to add heat. So think about putting a pot of water on a stove. You're adding a lot of energy to evaporate that. But what's a little harder to see is when we condense water, when we go from vapor back to liquid, that energy is released. And both of these are going to be very important for understanding both surface and atmospheric exchange, and also what happens to water when it's in the atmosphere. So we're not really working much with calories in this class. We want to work with kilograms. So we have to talk about another parameter, and we're going to call this lambda sub V, and this is the latent heat of vaporization. It's a constant. Oops. Vaporization. And it equals 2.5 times 10 to the 6, so 2.5 million joules per kilogram. It takes 2.5 million joules to evaporate a kilogram of water, and when we condense a kilogram of water, it gives off 2.5 million joules.